Welcome everybody, good to see you. Glad that you're here with me today. We're doing Pre-Calc 12 and we're talking about the applications of sinusoidal functions part 1. So this booklet here. And today we're going to be talking about the tsunami, the Ferris wheel, and a nail in the tire. I think that's what's in there. So if you look, the tsunami has a graph that looks like this. So we're talking about negative sign. The wheel, a nail in the tire of a wheel, so it punctures the tire at the bottom, and then it goes up top and goes around in a circle. So the position of the nail is at the bottom, it goes up, so that's a negative cosine graph over here. And then the Ferris wheel is a negative cosine graph, but it's shifted up a little bit, so we have like a vertical shift, and that's this guy over here. So those are the deals for today. Let me just make sure that these are the only things that we're going to be talking about, and then we'll get into our work. Okay, so here's our tsunami circumstance, and this book is basically, setting you up to be successful in dealing with modeling tsunamis and waves. Now, of course, we're dealing with perfect waves, and in reality, tsunamis don't behave perfectly, of course. But in order for us to understand the math, we have to assume that it's a perfect wave. So it's not exactly real, but it's pretty good, and it's a good way for us to understand how the argument works and how the math works. So I'm just going to remind you of a couple things about the tsunami, right? So when the tsunami hits, the water level decreases, right? If you've ever seen pictures of people standing on the seashore, the water level goes out and then comes back in a rush. So let's say you're standing on a dock, right, above the water. You'll see the water leave, so the height of that water, right, the height of that water will go down. You'll actually have a negative height of water. We'll talk about what that means in a moment. And then the water comes rushing back. So you're still standing on your dock. You're just measuring the height of the water at that moment in time. And then it comes back as a massive wave, and hopefully you're not in the vicinity when it hits where you're at. So that's the first iteration of what the wave looks like. And if you recall our formulas from last video or last assignment, right, we have A is equal to the top minus the bottom, K is equal to the top plus the bottom. Your B value for your equation is 360 divided by P. Sometimes you want to use radians, so it's 2 pi divided by P. And so we can use these formulas to help understand how to write our equation. So for example, like our horizontal phase shift, we're going to say is 0, so it'll be starting at time 0. And it's a negative sign graph, as you can see there. And K, your baseline, right, this guy over here, your baseline, how far it's shifted up, is dependent on where the water level is at the moment that the water starts going out. So I'm going to create a situation for us to consider, and then we'll work at creating the equation, and also we'll be doing some math about trying to figure out when it's safe and when it's not safe to be in the vicinity. Okay, so hold tight. Okay, so here's like what would be a typical word problem that you would see. I'll lift it up so you can make it out a little bit more clearly, and you can read it yourself. I'll give you some time. Okay, so we're saying at a dock, which is 4 meters above the ocean floor, a tsunami of period 20 minute makes a wave whose crest is 10 meters above the sea floor, or the ocean floor. Create the equation. Alright, so let's draw out a picture first and see what's going on. Okay, so here's a picture of it, right? It starts at time 0. We're 4 meters above the sea floor. We're going to be going, and what's going to happen now, and all we're doing is we're looking down at our feet and watching where the water goes, right? So the water's going to leave completely. It's going to, at this time, wherever that is right there, our seafloor is going to be exposed, right? And this area underneath here is when your seafloor is exposed. And what's one of the things we're going to calculate is how to figure out this distance in time, or this time interval. And then the water comes rushing back. I know it's the greatest sine graph, I know. And then it's going to come, and then it's going to finish off its iteration and then recede again. So there's a couple things we need to think about, right? First of all is, what's this value down here? Right? It's a theoretical value, because technically the water's not going to go below the seafloor. Like, you're not going to dig it up and then find the water below it or anything like that. It's a theoretical or an imaginary value. But we can actually we can calculate its value, because we know that a sine graph is symmetrical above and below. So you have to ask yourself, well, what's the distance between 4 and 10? Like, what's that range, right? So 10 minus 4 is 6. So this here is a distance of 6 going up. So going down, it's the same thing. So if I'm starting at 4 and I'm going to go down 6, then this value here is going to be minus 2. Right? I'm going to be minus 2. And that's going to be a theoretical value. That's the bottom of our wave. It's not where the water goes, but that's the bottom of our wave function. So this area underneath here is the area where, theoretically the water is below the surface of the Earth, which is like, that only works if you're a rock star for the Talking Heads or something like that. But this is the area where we see the seafloor, the starfishes and all that kind of stuff. And then comes back with a vengeance. Okay, so that's ultimately we're going to be able to calculate this little distance, and that's one of the things that we're going to lead to. So let's calculate the equation, right? We need to remember our formulas. So give me a moment, and let's do some calculations. Okay, so our job, right, is to be able to come up with values for A, B, H, and K. And if you remember from the very beginning of the lesson, H is 0 because there's no time shift left or right. And it's not always like that, but for us now, we'll use it like that. The only time it doesn't, the H value changes is when we talk about calendars, which is, I think, the coolest part of this whole job is doing the calendar stuff. Anyways, I'll get to there shortly. Okay, so I got to come up with the calculations for A, B, H, and K, and those formulas were at the beginning of the video. You can quickly scroll back if you want and find them, but I'll do the calculations down here so you can see them. You'd be doing the same thing too. Okay, so here are my calculations, and to be honest, you can get these values without really having to do a lot of calculation work, right? 6, right, if you remember back, that's the difference between the top and my baseline, right? So that's 6 right there. So yeah, I mean, you don't really have to think about it. You just, as long as you know what to look for, boom, there it is. Same thing for K, right? K is your baseline, which is, where your dock is at. And so you don't really have to work that hard to calculate those two. And if you can visualize those in your mind, then it saves you some calculations. And in the booklet, I get you to do some, matching questions where you're banging these things off, so it becomes part of your, your mental state. The only one that's kind of even remotely challenging is your B value, right? Your B value is 360 divided by P, or 2 pi divided by P, but 360 is easier to use for us for right now, so 360 over 20 is equal to 18. And that gives us the values for A, B, H, and K, because we know H is 0. Okay, so let's see what that equation looks like. Alright, so here's the equation, right? There's my A value, there's my B value, and there's my K value. And so there's my equation, and that's one of the jobs that I'm asking you to do today, is just to create the equation. But that's kind of just simple plug and chug. What's a little bit more crafty and skillful is to figure out some of the questions where we are required to do algebra. So moving forward, right, if I gave you a certain time, like say I gave you 8 minutes, you could plug in 8 there, and then you could calculate it all out, making sure your calculator's in degree mode, and you can find the height of the wave at time 8, or wherever you're at. But I want to work backwards, and one of the things I wanted to see was where or how long the seafloor is exposed. So what I'm thinking about here is, okay, well here's 4, -2, here's 0. Okay, here's the length of time that the seafloor is exposed, that time, right, because we're talking the height relative to time. Okay, so I want to figure out that change in t. So I got to be able to figure out this time value here and this time value there. Okay, so I'm going to give you a t-chart on how to execute that, because we're going to see this time and time again with all the other types of questions. Okay, so just give me a moment. Okay, so here's the start, right? How long is the seafloor exposed? So I want to find out when h is equal to 0. I'm going to get two values. I'm going to get one there and one there. And the difference in those time values is going to be the length of time that it takes to, for the seafloor to be exposed. Right? We talked about this -2 being like a theoretical point. Okay, so I just let h equal 0, and I need to go and solve for t. But solving for t is not as simple as it might seem. I have to sub out 18t for another variable. So I'm going to sub that out, and I'm going to go ahead and solve for the subbed out part. Okay, so I sub out 18t for big X, or whatever symbol you like. I always like my lambda, or whatever symbol you like. I've seen hearts and stars and stuff, so use what you like, but I'm going to use big X. And I got to solve for big X. Okay, so, I got to use the CAS rule and inverse sine and all that sort of stuff, -4 to both sides, the usual, right? And then I get a reference angle of 42 degrees, which gives me big X1 and big X2 are 42, 138. So, okay, that's fine, I've solved for big X. Now I've got to solve or turn those into t values. So, I got to sub for 18t back into those guys. Okay, so remember, right, 42, right, so big X, that's what we've got here, big X, right, is equal to 18t, 18 times t. So I have 42, which is my answer, is equal to 18t. So to solve that, I just got to divide both sides by 18, regular algebra, and I get t1 is equal to 7 I think it's 0.666 repeating. We'll just round it to 0.7. Okay, we could be more precise if we really wanted to, but that's fine for now. Same thing with t2. Actually, I got this backwards here. This is t2. And this is t1. Alright? Anyways, there we go. So 138 divided by 18 gets you 7.7. And where are we here? 42 divided by 18 gets you 2.3 minutes. So those are our time intervals. That's these points right here. Right? This is 2.3 and this is 7.7. So the difference in those times is the time interval. That's how long it is. So step 4, the last one, calculate delta t, or the change in t. t2 minus t1, right? The difference in time. But we have these values here, so I'm just going to go 7.7 minus 2.3, what's that, 5.4, something like that? So the change in t is equal to 5.4 minutes. That's how long your floor will be exposed. Now what's 0.4 of a minute? I think that's, you take 0.4 and you times it by 60. So that's the same as saying 5 minutes and 24 seconds. To be precise. Right, take that 5.4 and times it by 60, right? 0.4 of a minute is 0.4 times 60. So that's the general idea. Now this subbing in and out technique that we did here is going to be common for the entire rest of the booklet. When you do them for nail in a tire, when you do it for the Ferris wheel and for the calendars and all that stuff, you're going to be subbing in and out. So this is a technique we're going to see quite common from here on out. Okay? So I'm going to pause it and let's talk about the nail in the tire and the Ferris wheel. And I'm just going to go through the setup for you because you'll be doing the algebra on your own. Okay, so let's say I ask you to create the equation for the height of a nail in a tire if the tire has a diameter of 70 centimeters and rotates 15 times per minute. And we're assuming that the nail punctures the tire at the bottom when it hits. So okay, it hits at ground level, and it gets in the tire, it goes up the tire, gets to the top of the tire, and then it comes back down again, right? So that's a negative cosine graph. So what does the equation shape look like? Looks like this. Okay, so it's a negative cosine graph. If you recall your graph, so it goes up and then comes back down, right? Negative cosine graph. And so I have to calculate A, B, H, and K. But again, H is 0, right? Because it's starting at time 0. And so that's that. We don't have to worry about that. So I just need A, B, and K. So can you calculate them? See what you can do. This is what I got. And I did not make a mistake. Although you might think I did with my b value. You're like, b is 90? I got 24. What are you talking about, Mr. Gerard? Is that a ding for me? No, it's not. The thing is that usually you get information like this in terms of the frequency, right? So I'm rotating 15 times per minute. That means I'm going around the circle 15 times in a minute. But that's not the period. The period tells you how long it takes to go through one iteration, or one cycle of the tire. So how long is one rotation? Well, okay, so 50 seconds, 60 seconds in a minute. I'm doing it 15 times, so 60 divided by 15 is 4. Yeah, so my period, my p value, is equal to 4. And then when I plug it into 360 divided by p, right, 360 divided by 4, yeah, I get 90. Okay, now another interesting thing is that in this particular problem, your a and k values are the same number, right? Because your middle, right, is, you know, the distance is the average of 70, so that's 35, right? And then it's another 35 to get up to the top. So for the nail in the tire question, the a value and the k value are the same. Okay, so now I just plug it into the equation and let's see what we get. Okay, so there's my equation right down there at the bottom. And one of the things that I'm getting you to do is to think about, you know, finding out, like, I think one of the questions is, like, the air leaks out of the tire when the nail reaches a height of, like, say, 65 centimeters above the ground. The air will push it out. So the air will leak out of the tire over this time frame. Right? It's kind of like a tsunami, only on the other side of the bump. And so how long does it leak per revolution? Well, you're going to figure out delta t again, just like we did in the last question. So it's the whole process where you let h equal 65 over here. Come on. Right, 65. You got to sub out that for big X or whatever symbol you like, and then you got to do the whole process, and then solve for t, and then solve for delta t. So that's one of the types of questions that you're dealing with in your work today, is sorting that out. Okay, a couple of things to just quickly note. The a and the k are the same value. Okay, well, the a is negative because it's a negative cosine, but otherwise it's the same. And don't forget that usually the information is given to you in frequency in terms of, you know, certain amount of revolutions per minute. So you got to figure out the period, which is, you know, figure out how long it takes to do one cycle or one iteration of the wave. Okay, and then just plug in the parts as per usual. So let's look at the last one, which will be a Ferris wheel. Okay. All right, so I'm asking you to create the equation of a person's height. Okay, I gotta be like a person's height. On a Ferris wheel, if it has a radius of 21 meters, a 2-meter high platform, so you get on 2 meters above the ground, and rotates 12 times an hour. Right, so again, right, we know that you get on the bottom, you go to the top, and then you come back down again and you get off. It takes, does that 12 times an hour, right? So that's the frequency, and we got to remember the period of that. So the period, right, is equal to 60 minutes divided by 12, which is 5 minutes, right? It has a 5-minute period. So when I calculate my b value, it's going to be 360 divided by 5. Let's see what that is. 360 divided by 5 is 72. 72. So there's the b value. And we know that h is 0, right? So there's 0 there. It's not moving anywhere sideways. And then I have to figure out a and k. But so I know the bottom is 2, and I know that the radius is 21. So 2 plus 21 is 23, and then another 21 is, what, 44. And so I just got to think about radius instead of diameter this time. Okay, so my a value, I can calculate that. So 44 plus 2 is 46. So what's that, 23? And my k value is 44, sorry, 44, sorry, 40, I got this all wrong here. Hold on, let me calculate it. Give me a moment. There we go. So 21, right? Right there. This guy. That's the radius. And it's always the radius. That's one of the things about the amplitude. The amplitude and the radius wind up being the same thing. And the k value, that's your baseline. Well, we already calculated that. That's the middle, right? 2 plus the radius gets you to your baseline, because we know it's symmetrical. So bada bing, bada boom. Right? And so I know my b, a, and k. So I just plug them in there and I get my equation. Let's see what that looks like. Alright, so there's the equation right there. Plug them in. And so what I get you to do with that one, and I know it's really cheesy if you're kind of there and you're trying to work back from the video, I say, okay, well, so-and-so wants to propose marriage to his girlfriend. So he wants to propose on the Ferris wheel at the time of the sun setting. So he plans it just right. And so the sun sets at this height. So it's just a cheesy way for me to get you to do another delta t question. So how long does he have to pop the question? And if he blows it, his life will be ruined. Okay, not so much, but anyways. So that's kind of what the job is all about, is doing that. So in the next video, we'll do a solution for that, and we'll also look at calendars, because to be honest, calendars pretty awesome. We're going to do some sci-fi math. Sci-fi math. Yeah, it's awesome. Okay, so I'll talk to you later, guys. Take care.